So page 136 has this thing called atomic spectrum. Now, that's different than the visible spectrum. You guys know the visible spectrum, the order, right? Starts out at red, and it goes to the purple or violet. So when you would shine a light from the sun through a prism, you would get all of those colors continuous. You wouldn't get any gaps. Like on page 136, you guys see those gaps of darkness? When you get visible light, you don't get the gaps. Okay? You get the continuous spectrum. There's no gaps. And so what happens if I've got a substance and I heat it up, or in this case, on page 136, they're putting electricity through a gas. So they're adding energy to a gas. That gas has certain, depending upon what gas that they're putting electricity to, will have atoms, and those atoms have electrons. And those electrons, what they'll do, and this is called Bohr's model. I'm not going to have you know that for sure, but Bohr's model, when you do it, is going to kind of look like a planetary, the planetary solar system model. And we know electrons are not going to have specific orbits they're dealing with. Okay, so So in here we know we can symbolize the nucleus in here. So that's the nucleus, we already know. And we can have electrons located. And this is just a model. Okay? This is an atomic model. And the trouble with this model, it doesn't really work for electrons because electrons, they don't have nice, specific orbits where you can find the electrons. They kind of stay in this region, but this is so defined region. They usually call it a cloud because it could be anywhere within a certain region and not so specific. So here I'm showing an electron is really, really specific, and it helps us understand a little bit about how certain spectrum lines are given off. So if I take this electron and so I supply energy to the atom, and so let's say this line represents energy going in, and that could be different types of energy. Common ones would be heat, and it can also be like electricity. That's the ones we're going to use in here. So heat or electricity. So it goes in, and this atom will absorb that energy. Okay? So energy goes in, energy is absorbed. And so that's what we'll say, absorb that energy. And then what happens, these are different levels the electrons can be at. So this would be like level 1. This is like level 2 and level 3. Now,
so it can't go inside that other.
Right. It can't exist in between the two levels. So electron has to be. It's kind of like this, and it's kind of a easy example to work with. So I go to the vending machine. Something costs $1, and I put in, say, 50 cents, and I hit the numbers. Am I going to get that object? No. So if it absorbs energy and this electron doesn't get enough energy to go to that next level, it stays where it's at.
So the electron is just a little black dot.
That's the symbol of it. Okay.
Well,
so it's that
so
this is the electron.
Circle the nucleus, or is that all the black dots?
Yeah, this is the electrons, and these are the protons and neutrons. Okay. And so I'd have to put at least $1 in to get the object out. And so this has to absorb enough energy to get the object to move from here to up above here. It's kind of like a book. If I have a book on the ground, and this is, I mean, duh, I can lift it up. Or lifting weights. You lift it up and put it there, then that's enough energy. But if I can only lift it up, it's really heavy to here, and I can't, or something really, really heavy I'm trying to lift, and there's no way I can lift on my own. It's going to stay at that level until I'm able to get enough energy to lift it up to that next level. And that next level will stay for a short period of time. So the energy goes in, this electron's going to go up here, but it won't stay up there. That electron won't stay up at this level. What will happen is it will fall down sometime during the process of energy and being added, because we've got lots and lots of atoms this is happening to. So if it falls down, the energy that takes place when it falls down has to be released. And that energy is released as a photon of energy, and that photon is a bundle of energy, and it might have a wavelength, something similar to that. Okay? So now we have a prism here that's going to go through, and it might split off, and then it might give you, say, red. I'm just showing that as an example. Okay? So that energy goes off, and you just get red. You don't get the whole visible spectrum. So let's say I put in more energy, or there's a lot of energy going in. It's kind of like a vending machine where you put in $10 and you can hit 75 cents, you can get $1.50, you can get the one for $2.25, you can just keep going. But each one requires so much energy. And so let's say this is like $10 going in, and that energy able to take those electrons and move them here and down, which is vending machine, wouldn't be very much. But then it could go up here to this spot. Well, if it goes up there to that spot and it drops back down to, let's say, here, before it transitions down to the ground level, which it's probably eventually going to do, this is another energy that's going to be sent off. So let's say that that's sent off, and let's say that's a higher energy drop. So what's my wave going to look like if it's a higher energy? Is it going to be shorter or longer? Shorter, yeah. So it's going to be shorter, and it's going to go like this. And that light's going to go on all directions, and it goes in here. And so maybe that comes off, and now that is green. Now, there's a gap there, and that will be black. So there'll be a line that's red here, and there'll be a line that's green there, and this is black. Okay? So then, let's say that we have that same electron in another atom. This would be like multiple atoms. It goes up here, and then it drops down here. All in one swoop, eventually. So what kind of wavelength is that going to be? Shorter yet, right?
Yeah.
Okay. So we'll make it really short. Gets there, and then that's going to be a higher frequency wave with a shorter wavelength. And so that will split down to here, and that might be your violet. And that might be all the lines you get off.
Wait, is red or green? Which one was for green? The top line?
Yeah, the red is the long wavelength, so this would have been the red.
Okay.
And this would have been the green. And then this would have been the violet. Now, this is just, I'm not saying that this would ever happen to any atom because I'm being really specific. And you guys see spectrum lines there on page 136? You see those? Each of those represents an electron moving from one energy to another. Okay? And that's the idea behind spectrum lines, and no atom's alike, because every atom has different number of electrons at different locations, and they have different jumps. I'm just showing one electron, but if you have something with multiple electrons, you've got multiple jumps. We even have jumps that would go outside of our visual light. So we've got visual light we can see, red to violet. But you could have ultraviolet ones that are sent off, that's down here that we can't see. We can have infrared ones that are longer wavelengths that they won't show up in the visible spectrum. And so that's what we're going to kind of really talk about. There's levels where electrons are located, and they're called principal energy levels. So level 1 is the closest to the nucleus. It's called the ground level. All right. Now I'll reiterate this for those who are gone today, and we'll relook at this real quick. But this 1 would be the lowest level. Be the lowest level. It'd be like ground floor. Your ground floor in here. Level 2 would be higher. Level 3 would be higher yet. Okay? And then as the bigger the drops, the more energy that the atom would give off. And that's why you get all the different colors out, fireworks. Get the purples and reds and orange and whatever those are, silver. You get all those colors out, and that's because of this idea of excited atoms, and then when they give off the light, then you get those different colors. So if you look, page 136, it talks about principal quantum number N. So when we get in just talking about the principal quantum number, we have what's called the principal quantum number. And it's symbolized with the letter N. So N is positive integers. So it can be 1, 2, 3, 4. And it represents the level, energy level of the electron. Okay? So a 2 is higher than a 1. It's farther away. A 3 is higher than a 2, farther away. On our drawing we had 1 closest to, and so on and so forth. So that's called the principal energy level, and the higher you go, the more energy that the electron is going to have. And that's what it talks about on page 136. The changes of energy levels on 137 I kind of showed you with the atom. If you turn over to page 138, tomorrow, or Friday, we'll get into these things called sub-levels. Alright? So you got level, and within a level you got a sub-level. So, we're not going to get into that today. But sub-levels, electrons take on different shapes around the nucleus. So, that's kind of what we call as a sub-level. And there's 4 types of sub-levels. There's an S sub-level, a P, a D, and an F. And then we'll talk about those shapes and those sub-level shapes and give you some visual descriptions of those shapes as well. So, we won't get into sub-levels, but this is principal energy, quantum number represents the energy level that you have. Okay, that's all I'm going to talk and visit with you about. If you want to, you can start looking at page 138 through 141, and it kind of goes through some of the specifics about electrons. It gets into their shapes and gets into actual spins and those type of things. So we'll visit about that on Friday. Okay. Tomorrow's a lab. You come in, we'll have you sit down, we'll talk a little bit about specifics about the lab, have you go do the lab, and then there's some questions to answer after you get the lab done. So, okay.